Right. Okay, so we are in chapter 8, FSMs and data paths. In chapter 4, I just want to do a quick recap. In chapter 4, we have seen combinational circuits, multiplexers, decoders, full adder, encoder, and so on. These are the logical blocks that we give set of inputs. We do some operations and it will produce set of outputs depending on the specifications. And we can use this without a clock and there's no feedback path. Okay, so whenever the input changes, output changes. Then in chapter 5, we have introduced a clock with a feedback path. So we have got the present state and the next state. So the next state is affected from both from the inputs, which is like a combinational logic, and also from the present state, which is from the feedback path. And these are all working with a storage device, which we call flip-flops, that they are working with the clocked devices, clocked memory cells, that we can store the present state and we can use it. And when we combine these things up, in chapter 6, we have seen that we can implement counters, registers, shift registers, and different types of counters and so on. Now, these are all together forms a system. Now, we started from the basics, from the gates or the transistors, let's say. Then we put on the gates. So when we combine transistors, we generate gates, we construct gates. And from those gates, based on the specifications given, we can construct logical blocks like combinational or sequential blocks. And depending on the architecture, these can be 4 bits, 8 bits, 16 bits, 32 bits, 64 bits, and so on. It goes like that. Now, in this chapter, we are taking this one level up, okay? So it's more higher level compared to the previous chapters. Now, what we are going to see in this chapter, now, when we consider a digital system, okay, or if you want to specify a large digital system, now, this type of digital systems has got a combination of all of these together. Chapter 4, the combinational circuit part in there, Chapter 5, sequential circuit part in there, and Chapter 6, where you have a bigger circuit. Now, in order to specify a large digital system, like we have done it with the truth tables and the state tables, it is very difficult because the number of states that we can define will be enormous. And in order to overcome this difficulty, digital systems are designed with a modular approach. So what are those approaches? Now, the system is partitioned into modules, subsystems, and each of which performs some functions. Okay, so we can specify actually which function is going to be performed in which module. And the modules that are constructed from are coming from the previous chapters. We are building digital devices like registers, decoders, multiplexers, and putting all them together. And these various modules are actually going to be interconnected with data path because we actually define how the data is entering into the system, how it is going to be processed or stored, and then we actually also need to specify a control in order to decide when to get fit in the new data, when to perform the operation, and when to send it to the output, and so on. So digital system in general, let's say this is a digital system itself. What do we have here? We have got a data path unit. Now, inside of the data path, we have got combination of uh, registers, decoders, maxes, and so on. So chapter 4 and chapter 5 in there. Okay, the logic blocks that are working with the clock or without the clock. Now, on the other side, we also need some kind of a brain of the system, which actually going to talk to the data path with some uh, control signals that telling the data path, okay, do addition, for example, or load the register. So these are all coming from the control unit. Okay, so this is how we are approaching to a large digital systems. We divide them into modules. The data path is on one side, which we have seen all of the components of the data path, and we have got the control unit on the other side. So this is what we are going to concentrate, because as we already know most of the data path size, we don't know how this control unit or the control logic is going to be implemented. So the formal definition for the data path, processing logic and registers used to stage, temporarily store and pipeline the process data. The data flows through the data path through a simple register to register movements referred as register transfers, and the combination of logic blocks between the registers help to perform micro operations. So we are actually doing register transfer level operations over here, and we are actually doing micro operations. On the other side of the data path, the control unit, it drives a sequence of data processing operations performed by the data. Actually, the control unit is controlling everything flowing in the data path. It's actually the brain of the system. Okay, so the operations in a digital system are controlled by timing signals that sequence the operations in a prescribed manner. And the outputs of these control logic are binary variables that initiate the various operations in the system registers. So these are all binary variables, let's say control signals. Okay, so these are all sent out by the control logic. And we actually have a feedback which is showing the status of the data path, telling, okay, I'm ready for the next operation or something like that. We can also have control inputs coming from outside. And we can have data inputs coming outside. And also we send out data. And everything is happening inside of the digital system. We might also have some control outputs from the control unit if we are going to have any other part of the system. So when we want to talk about digital systems, this is a typical digital system which we already designed over here as well. The information transfer from inside of the register or from the system is generally happening with the register transfers. So, for example, typical example of the register transfer is, let's say, R2, oops, other way around, R1. So what does this is doing? The contents of R1 will be transferred into R2 or copied into R2. So R2 will have the contents of R1. Now, the control unit or the control signal will actually determine when this operation is going to be performed in the data path. So this is what we are defining in the digital systems or in the control units. Now, control units, which we are interested in this chapter, is also known as FSM. Now, what is FSM? FSM is known as finite state machine. So it's actually another name used for the control unit. We have got over here a finite number of states when we want to define the control unit. And the sequential circuit is actually represented with a finite number of states. And it's made up of FSM and FSM, or the finite state machine, used for control unit in general. So far, we have seen how a digital system is constructed. We have got the data path, we have got the control unit and some control inputs, control signals to the data path, status signals are coming out, control outputs, data in, data out, and so on. When we consider digital systems, we consider these register transfers, and we consider how these register transfers are going to be operated and when. And the easiest way of understanding these digital systems, I think it's good to show a simple example. So here is a digital system design, which we have got adder subtractor example. And in a typical system, we want a register transfer operation to occur not with every clock cycle, but only under predetermined conditions. For example, I can say if t is equals 1, then copy R1 to R2. Okay, so we can have these conditions. So if t is equals 1, then we can have R2, R1. Or maybe if t equals 1, then R2, R1, and or maybe R2 is copied into R1. Or maybe something else like R1 is R1 plus R2. Now what is happening here? R2 and R1 is added together and the result is stored in R1. If you do remember in chapter 1, where we have talked about registers and how these things are transferred between the registers, this was one of the operations over there. And we can have another one like R3 is R3 plus 1. This is increment. This is add. And another one, R4, can be shifted right and store the result in R4. Now, these are all data path operations. And the last one, let's give this example as well, 0. So we are clearing the register R5. So these are all data path operations, but data path itself is nothing because we have to say, we have to specify which operations do we need to do and when to do. Okay, and for example, in hardware, addition is done by a binary parallel adder, incrementing is done with a counter, and the shift operation is done with a shift register. We have seen these in chapter 4 and 5. And the type of operations in digital systems like copy data from one register to another, arithmetic operations, logical operations, and shift operations. We can perform all of these together. Now, I'm going to show you a data path unit as an example, which is the adder subtractor. And we will decide how the control logic is generating the signals for sequencing these operations. And the control commands for the system, which are derived from the control unit, are produced as a function of the FSM, as the primary inputs, and the status signals and the state of the machine. And the control sequence and the data path task of a digital systems are specified by means of hardware algorithms. Now, we are actually specifying a hardware algorithm, which we actually have what do we call as a hardware algorithm? It's a procedure of solving a complex problem with a given piece of equipment. We have a data path that we have to do add and subtract, and we have to use this data path in a harmony that we can produce the result efficiently. And we have to make sure that everything is running smoothly inside of the data path without any data lost or without any data crash. Now, when we consider the digital logic design, it is the most challenging and also the creative part of digital design is the formulation of hardware algorithms for achieving required objectives. So this is what we are going to do. We are going to do some creative and challenging stuff to make the hardware which is inside of the data path to work in an harmony. This is what we are going to see in this chapter. Okay, so let's see the data path. Data path is here. In the control FSM, we have got two control inputs, start and subtract. And the control FSM is generating reset, add, subtract, load register 2, load register 1 to the data path. These are sended. So these are the control signals. We have got 4-bit input and 4-bit output. So this is what we have got inside of the data path now. This is what we have got. So R2 is the first register. We have got adder subtractor over here. R1 is the second register. Load R2 signal is feeding into the R2. Reset is there. Load R1 is over here. We have got a carry signal. Add and subtract control signal is over here. And we are going to do these operations one by one. Now, in a typical system, when we look at this, we should specify how these are going to work together in the data path. And we can specify these with the micro operations. But let's see the problem description first. Given the system and below the data path block diagram, derive the state diagram for the control unit FSM required to load two 4-bit numbers to R1 and R2 and then do addition or subtraction between them. Depending on the status of the control unit, subtract input 1 for subtraction and 0 for addition. Note the adder subtractor unit either adds or subtracts, but cannot perform any other operation. So this is just making our lives easier. We just need to perform add and subtract. Assume the FSM resets back to the initial state if or when the start is deasserted and reset is synchronous, which is working with the clock. Okay, so what kind of micro operations we are required? So let's start with the first one. Now, when we are powering up a system, as the registers or the clocks are not making any operations yet, the register values are just all high impedance, the logic values are high impedance. So what we can do is we can initialize these registers. We can reset them to 0. So in the time sequence 0, I can say that. Let's do it this way. Micro operations. So in the first time sequence, we can say that I want to reset R1 and R2. Let's say this is initialize. So in the first time step, we reset our registers because we can clear the registers if we are starting from the beginning, or if we are going to start to a new operation, we make sure that we don't have anything stored in the registers. So we initialize it, we clear the registers. Then next thing to do, we have to load data into R2. Okay, because R2 is the first register that the data from the outside is going to be loaded in. So we can say that in time step 1, R2 will have the value of data in. So we can say load first number. Then, in the second time step, this R2 has to pass the value down to R1 so that I can retrieve the new 4-bit number, because I'm going to add both together. So how is the data path is going to pass this R2 value down to R1? Now what will happen is, as we have initialized this, at the beginning, I'll just do it over here. Now the register value R1 is 0 and R2 is 0. Then R2 has the value, let's say, X, and R1 is still 0. Now in time step 2, where we are going to say, okay, copy R2 into R1 and get this new data into R2. Now what will happen, as R2 is going to pass down and R1 is feeding back in to the other subtractor, at this point it's actually going to do R1 equals X plus 0, which will be equal to X. So the X value is now in R1. This is how it is copied. So we can say load second number. Okay, so X plus 0 will give us X. Now the R2, R1 has got X, and at this point R1 is equals X, and R2, as the new data is coming in, it will be equal to, let's say, Y. So we have got two numbers, two 4-bit numbers stored in the registers. We have got them in the data path. Now, we have got two options. Either we do an add operation or we do a subtract operation. So in time step 3a, let's do addition. Now, when we do addition, we are going to add R1 and R2, but as you can see, like we have done it over here as well, R1 will be fed in and the result is stored in R1. Okay, so R2 and R1 will be added and the result will be stored in R1. So R1 will have the value R1 plus R2. So this is adding R1 and R2 and store in R1. Okay, or alternatively, what we can do is we can do a subtraction. So how do we do the subtraction in digital logic? We have to take the complement of R2 if we are subtracting R1 minus R2. So this is going to be R1, R1. We are doing always addition. Make sure that you do remember that from chapter 2, chapter 1. And the complement of R2, invert, and add 1. Okay, so this is actually going to do a subtract R2 from R1 and store in R1. Okay, so this is the subtract operation that we perform. Now, we have identified the micro operations required for this data path. We know the control signals, which is given in the specs. And then all we need to do is we have to derive a FSM state diagram to show how the control signals are changing the states of the data path. So let's show the operations here as well so that we can use that as a reference. Now, how many inputs do we have? We have got 2 inputs. What are those inputs which are coming externally? If I go back, start and subtract, because we are considering this part now, we have got start and subtract. So start, I'll say ST, and subtract, I'll say sub. Okay, these are the 2 inputs. And how many outputs? We have got these as an outputs, which are the control signals, and we can put them in an order. So 4 outputs. I'm putting them in an order that I'm going to use them. So I'll say add or subtract, load R2, load, I'm just writing short notations, R1, and reset. So these are our outputs from the FSM. Now, as we have got 2 inputs and 4 outputs, we now know where to start from and how to start. So to draw the state diagram, as the specifications is given, the other subtractor unit either adds or subtracts but cannot perform any other operation. Assume the FSM resets back to initial state if when start is deasserted. So that means the first state with the micro operations, we have to reset the registers and we have to wait start to be asserted. That's what it's saying. So I'll create state 0. Okay, and when start is deasserted, I have to wait there. But while I'm waiting there, going with this order, and as my states are going to change, my outputs are going to change with the state, this is a Moore machine, so I have to write my outputs inside of the circle. So add and subtract, I'm not going to do any operation, assume it as 0. Loading R2 will be 0. I don't want to load anything while I'm resetting. Load R1, it's also 0. Reset, it has to be 1. It's working with the clock. Whenever the reset is 1, it will reset my 2 registers to be 0. Now S0 completed. Now, next thing that we need to consider is S1. Now, how is that S1 is going to work? the next state. The next state is we have to load data into R2. So when the start is asserted, we can go to next state. Okay, asserted. And when we are in S1, if it is deasserted, I have to go back because I'm not going to do any operation. Everything is working with the start. So when we are in S1, we have to load data into R2. So add and subtract, still 0. Load R2 has to be 1, as I need to activate this register in order to load something in there. Load R1, I don't need to load anything at the moment, and reset is also 0. Now S1 completed. Let's move to the next one, where we have to load data into R2 and copy the R2 content into R1. So I'll say S2 over here. Again, start is still asserted. And if it is deasserted, it has to go back. Now, over here, add and subtract will be 0 because if you do remember here, we are performing this operation, so we are actually doing an add operation. So 0, load R2, as we are loading new data in, it has to be 1. Load R1 has to be 1. Reset has to be 0. So we are actually performing the second time step micro operation, which is copying data into R2 and copying R2 value into R1, the previous value. So far, they're just straightforward loading the register, resetting and loading the registers. Now, we will take this further. Now, 3A is actually doing an add operation. So, S3, I'll say. And start is asserted. And also, from the specs, it says addition is 0. Okay, so that means the sub, which is coming externally here, it has to be inverted. So I can say sub is inverted. Now what will happen as an output as a control signals? Add should be 0 because we have to perform add. Load R2, we don't need to load anything into R2, but as we are doing the operation and save the result into R1, we have to activate the load R1 and reset is 0. So that's S3 state. And then we'll have S4, which we can need to create alternative for subtract operation. Start is asserted, and this is sub, not inverted. When sub is 1, that means the control signal at sub is 1, load R2 is 0, load R1 is 1, reset is 0. So load R1, again, it has to be 1 in order to activate R1 so the result can be stored. Now we have got the steps or the micro operations required generated as a state diagram. The last thing that we need to consider, now what will happen if the start is still asserted after state S3 or state S4? They can go into the common one, nothing will change, it's like a hold state. So it can go to S5, start is still asserted, but no other operation, okay? And over here as well, because it's hold, start is 1, just wait there if you are not going to do any other operation. Whenever the start is deasserted, it has to go back, reset the registers, and start again. So the outputs, as we are not going to do any arithmetic operation, we are not going to load R2, we are not going to load R1, we are not resetting, they are all zeros. It's just waiting there until start is deasserted so that we can go back and start again. So this is how we can generate a state diagram based on the specifications given and with the micro operations. So you can see the similar state diagram here in the lecture slides. Now, one thing that we need to be considering, data and control signals need to be set up in advance before data transfer can happen into a register. And one clock setups the data and control, and the next clock latches in the data. So we have to be careful over there.